Hey guys, welcome back to UVM Testbench code from scratch for the D Flipflop design. Let us move on to the further code of UVM Testbench. So far we have seen build phase and connect phase of the different UVM components. Now let us see the further concepts. Once the DUT as well as interface is declared in the Testbench top module, we need to set the interface into the config DB. So UVM configuration database allows us to set that interface in the top module first, and then the lower components can get that easily. So within the initial block, I am setting the UVM config DB here using UVM underscore config underscore DB. We need to pass the name of the interface, that is virtual DFF underscore INTF colon. We need to use the set method here to set the interface into the configuration database. Set, it takes 4 arguments. First one is null. You can also write UVM root over here. So then the second argument is star. This star allows the interface which you are going to set into the configuration database to get in all the lower components. That's why we are going to use star. Suppose we are setting this to particular component, then you can mention that over here. Then the third argument is VIF. VIF is the key for the configuration database. Using this key, the other lower components are going to get. And INTF is the INTF handle which I have used here in the declaration or instantiation of my interface. So once we set in the top module, we are going to get this interface in the driver and monitor class. In the driver class, you can see in the build phase, I am going to write get configuration database. UVM config DB virtual DFF underscore INTF. Here I am using get method. Get, where I am getting in this class, and VIF is the key which I have used while setting. INTF is the handle. And remember, in the driver and monitor, the interface is a virtual interface. The physical interface we can't use over here. Since it is a dynamic component, we need to use the virtual interface in the driver as well as in the monitor. So virtual DFF underscore INTF with the handle INTF. So I am passing that handle here. This is how we can get the interface in the driver from the configuration database. If the interface getting failed, we need to stop the simulation. That's why I am triggering UVM fatal here. You can also write UVM error, but better to write UVM fatal since this interface having all the signals of our DUT. So once we fail to get that in the driver itself, no further simulation will occur. That's why UVM fatal is used, and here we need to write the display message. And similarly in the monitor also I am defining my interface as virtual interface with INTF, and in the build phase I am going to get the interface handle from the configuration database. Again, if it fails, I am triggering UVM fatal. This is how we can set the interface from the top module, and we are trying to get in the driver and monitor. If it fails, we need to trigger the UVM fatal. Then let us move on to the other classes and see the next phases. Build phase is completed. In the build phase, we are going to create the lower components using type ID create method. In the connect phase, we are going to connect the lower components, but in the test will not be any connection made. So simply I have written the connect phase here. It is not required also. Next comes end of elaboration phase. This end of elaboration phase is going to give you the UVM hierarchy. You have defined all the lower components and how they are connected each other. What is the hierarchy of UVM that you can print using end of elaboration phase. So in the end of elaboration phase, I have used print method. This print method gives you the UVM hierarchy in your log, simulation log. Then comes the run phase. So run phase is a task. Run phase is always defined as a task. Why? Because this run phase is the heart of simulation. So run phase consumes much time. All the transactions flow will be in the run phase itself. So task run phase, UVM phase. Here we need to start our sequence. We need to start our sequence over here. SEQ is the sequence, DFF sequence. I am giving the handle as SEQ. That's why SEQ dot start. I am starting that sequence. On which sequencer we need to start. That's why environment agent sequencer. It means SEQR is the handle of my sequencer. It is not there over here. Sequencer present in inside agent. So in the agent class, you can see sequencer is defined and the handle is SEQR. That's why here environment under that agent is there, under that sequencer is there. That's why I am giving the complete path since SEQR is not available in the test. This is how we can start our sequence. So before that, what we need to do to give a time to complete this sequence, we need to raise the objection, phase.raise objection in this class. Stay in the run phase until the test dropping the objection. Means the simulation should be there in the run phase itself until this sequence get completed. Once it is completed, then drop the objection. That is what we are writing here, raise objection and drop objection. If you are not going to raise and drop the objection, simulation may get over in less time. Then coming to the next component, environment. In environment, we have connected the lower components, that is monitor and scoreboard using analysis ports. Here there is no requirement of run phase. Then comes driver. In the driver, run phase is very much required and it is very important phase. In the run phase of the driver, what we are going to do? Give the transaction which we are going to get into the DUT. That's fine. Here you can see sequence item port is the port of the driver. Get the next item of the transaction. And after getting the next item from the port, we need to drive that. So how we are going to drive? This is the drive task I have written here. Otherwise, you can write all these in between the lines here also. So here is the drive task. What it will do? It will take the transaction. The transaction will be consisting of reset D as well as Q, and we are passing that to the interface handles. Interface reset, interface D and interface Q. This is how driver will give the transaction to the interface signal. And then from the sequence item port, we need to send the message as item done. So for this, we need to understand the communication between the sequence, sequencer and driver. You can see I am explaining driver. This driver will communicate with the sequencer as well as the sequence. So driver get the next item. It will request the sequence item from the sequencer. Sequencer will give that information to the sequence. The sequence will randomize and then they send the request to the sequencer, sending the sequence item to the driver. And driver then it gives to the DUT through the interface. And similarly, the response will be come from the DUT to the driver, and driver will send the item done information to the sequence. This is how the run phase of sequence, sequencer and driver works. So now in the sequence, if you look at the sequence, in the sequence we need to have our transaction, that is sequence item, and sequence is an object class, though there will be no phases. Here we need to write a task body task. This body task will do this functionality of the sequence. What it will do? First it will create the transaction using type ID create method. Here I am creating the transaction. TX is the handle for the sequence item. Then what it will do? It will wait for grant. This wait for grant signal is the request from the driver, requesting sequence item from the driver. So in the driver class, you can see it is requesting the get the next item. That is the request to the sequencer. Sequencer will send grant to the sequence and our sequence will wait for that grant. Once the grant is achieved, once the grant is received, then it will randomize. tx.randomize, it will randomize the transaction and it will send that request transaction to the sequencer. That sequencer will send to the driver. This sequencer functionality is default. We are not going to write the sequencer functionality in the UVM code. The sequencer functionality is by default in the UVM. So in the sequence, we have randomized and send the request and wait for item done, so to generate the next random transaction. So this wait for item done will be getting from the driver. Driver, you can see it will do this functionality and then it will say the item done from the port. This will make the sequence to again generate the next transaction. So here I am repeating this for 5 times. So it will generate 5 transactions and it will send to the driver. Then driver, what it will do? It will give that to the interface and interface will pass that to the DUT. This is how the communication of driver, sequence and sequencer happens. Now in the monitor will connect the response from the interface and it will give it to the scoreboard. So the monitor and scoreboard are connected. So the monitor scoreboard connection we have made in the environment. You can see here we have made the connection using item collected port as well as item collected export of the scoreboard. These are analysis ports. We don't have these ports available. That's why in the monitor you can see here I have used UVM analysis port and I have created this item collected port here. UVM analysis port, it will take this transaction and it will be act as item collected port in this class. So item collected port we need to create over here using new method I have created. Similarly, in the scoreboard, you can see using UVM analysis implementation port, we need to create item collected export. This item collected export I have created using new method here. Now those two are connected in the environment. This environment makes the connection between monitor and scoreboard. Now monitor will collect all the response from the DUT and it will pass it to the scoreboard. So monitor, you can see here in the run phase of the monitor, what we need to do, at positive edge of the clock, it will sample the outputs. So it will take all the values from the interface and it will take into the transaction. So this is how the monitor will do. And then coming to the scoreboard, in the scoreboard, what we are going to do, we need to put that all into the queue. We need to have a write method, that is write function. This write function is going to use the queue that we have defined it as the DFF sequence item, that is transaction queue. This transaction queue we are going to use to push all the packets received from the monitor, and this queue will be used for the decision. This is how the scoreboard is going to work, and let us see the scoreboard functionality in the other video. Now let us run this code and see how the transactions are going to be generated and how we are going to see the UVM tree. So you can see here now the simulation has got completed. So now we can see the UVM hierarchy over here. This is the UVM tree which we have generated from the end of elaboration phase. DFF test, environment, agent, driver and all the ports, monitor, sequencer you can see over here. And if you come below, you can see here the clock is generated. I have just displayed the clock. It is generated in the run phase, you can see. And if you come down, it will display the report by severity. UVM info we have used 32. There is no UVM warning from our code. There is no UVM error. There is no UVM fatal. And you can see how the execution will be. This is the constructor and build phase, connect phase, all come under UVM info. If you open the EP wave, you can see the generated waveform. So here is the waveform. This gives D is equal to 1 and D is not randomized fully. Let me randomize. Let me increase this to 10 and run it again. So now you can see D is randomized let me take this reset to the top. I have used the constraint to keep this reset 0 always. That's why reset has not randomized throughout our simulation. And you can see input D is randomized here. Up to here input D is 1, and you can see here the output is changed to 1, and once input D becomes 0, in the next cycle the output will be changed to 0. Again here D becomes 1, the output is going high. So this is a simple code to verify the D flip-flop, and here the scoreboard code is not written completely. Let us see this scoreboard functionality and let us write the test pass fail depending on the functionality of the DUT. Let us see that in the next video. Thank you.